And of course, at any point, if you do have any questions over concepts you were going over, maybe during the break, feel free to ask that. I know I already have a recording of this session, but once again, this is for those who would rather have, a live session. So, yeah. Anyways, so calculating molar mass is one of those things that we have to know in chemistry. The molar mass is important because it helps us in chemistry figure out the amount of the chemical we're dealing with. So let me make sure I have my 3-point check. It looks like I'm recording. You can hear me, and I'm sharing my screen. I'm trying to make this more of a habit versus just assuming it's done. Okay. The molecular mass. So sometimes it's called a formula mass or a molecular mass. With a formula mass, it's a lot easier to understand that because it's pretty much the mass of the formula that's provided to you. With a molecular mass, though, all they're communicating here is the mass of the molecule, and essentially the molecule still describes the formula of the compound. Okay. Now it can be, if it's a formula mass, that's more generic because that could be a compound or an element. Bottom line, the mass of whatever chemical you're dealing with. So you see terms like formula mass, molecular mass, or molar mass. And it's implied that you're always working with a 1 mole amount of that compound or element. Okay. So why is 1 mole selected? 1 mole is selected because all the masses, so all atomic masses reported on the periodic table are for 1 mole of the element. Okay. So remember, at this point right now, I don't remember if we've defined what 1 mole is. I'm going to operate out of the assumption we have not defined what 1 mole is. So 1 mole is an amount. It would be like saying, not really 1 kilogram, but 1 ton. Okay. The term mole stands for a certain amount of items. In this case, the context is a compound. So it would be like saying a pair of scissors or a dozen of eggs. The word dozen stands in place of the number 12, right? Or let's say a week, referring to time. Okay. So the term here, mole, is a word that replaces the number, Avogadro's number, 6.02 times 10 power 23 number of things. Okay, so it can be items, it can be clothes. This is too much for us to comprehend. It can be people, it can be elements, it can be compounds. The context here, of course, in the chemistry will always be compounds or elements. Okay. So, once again, the masses reported in the periodic table are masses, they are average masses for 1 mole of that element. So when we're dealing with molecular mass, the macro level masses, we tend to report the masses. It's understood as for 1 mole of the compound. So, understanding that when they're asking you what is the molecular mass for water, what you're reporting there is the mass of water. If you take 1 mole of water and you got the Avogadro number of water molecules, that would be 6.022 times 10 power 23 molecules, individual molecules, and you put them all in the same container and you weighed them, the scale will read 18.02 grams. So it takes 1 mole amount of water molecules to produce this amount here. And they show you how they calculate this. It's based on the formula. So water has H2O, 2 hydrogens, 1 oxygen. They take the mass of hydrogen from the periodic table. Like I told you, the masses listed in the periodic table are the masses of 1 mole of the element. So they are taking the mass of the components to get the mass of the compound. Okay? That's how they get that here. And you have the generic form here. So what I want to do right now is to go over how we go from the molar mass to molecules. So we're being told here, you can go from the molar mass, or actually you can go from the grams given. So this is a conversion pathway from grams given to molecules. So in this conversion pathway, this is similar to what we've seen before. We went from grams of element to molecules of element, only now the context is grams of compound to molecules of compound. So from grams to moles, your conversion here will be the periodic table molar mass. You can see that right here. For moles to molecule, here you will use the molar conversion, which says 1 mole of the compound, I'll call this X, equals 6.022 times 10 power 23 molecules. Okay, so in context, in this problem here, I will show you, of course, once again, how to figure out the molar mass as we're working on this problem. Okay, because I figure out, as far as getting the molar mass is concerned, that's a lot more straightforward. It's the conversions that get more complicated. Okay, so we're going to go from grams to moles, from moles to molecules. You cannot go from grams to moles directly if you're trying to use the proper conversion pathway. If you do that, you're going to be going online and Googling something, right? We don't go directly from grams to moles, grams to molecules bypassing moles. We go from grams to moles, then moles to molecules. Okay, so I'm going to be working on this problem right here. This is an application problem. Context here, grams to moles, and then moles to molecules. Okay, so I'm quickly recapping what I know. From grams to moles, we tend to use our periodic table mass conversion of the formula, whatever that is. And then moles to molecule, we use the Avogadro's conversion. So I'm going to write here Avogadro's conversion in short form. Okay. So before I read the question, based on the title, I'm writing what my tools are. I'm going from grams to moles, from moles to molecules. Okay. And so we're told here, an aspirin tablet contains 325 milligrams. So I pause for a second and say, wait a minute. Am I not supposed to start from grams? Then I answer myself in this monologue, yes, I am. Okay. But they gave me milligrams. Yes, they did. So that means I need to add one more conversion to get my number right. Okay. You have to have your number in the right unit. So I would like to start from grams, but they gave me milligrams. So I essentially have to add one more conversion, go from milligrams to grams, and then grams to moles and moles to molecules. So this is the path I know of. And if my number is given to me in a path that's opposite or different from what I'm used to, I just have to prep my number to get to the path. Okay. So milligrams, I know how to deal with that. Acetylsalicylic acid, the formula is given to me right here. How many acetylsalicylic acid molecules does it contain? Okay. I'm going to add a page right here and start working this out. So I know my regular conversion, I've highlighted it here. Now I have to add the milligram to gram. So I'll start off by listing what I have, right? So what is given in my question is I'm given the amount 325 milligram. And what is the chemical? Acetylsalicylic acid. I really need the formula. So C9H8O4. Okay, so I'm given this amount here. What they want, so right here, wanted, is they want some number. The units has to be molecules, right? They said so right here, of C9H8O4. Okay, so when I do my conversion, I do my math, everything, I should end up with the unit molecules of C9H8O4, right? Okay, now how do we go from milligrams to molecules? So here's where I start writing my conversion. I know where I'm starting, I know where I'm ending. Now I'm writing my conversion. Okay, the regular conversion. So I'm going to start with the regular one, right? Goes from grams to moles, from moles to molecules. Okay, so from grams to moles, I know my conversion here has to be my periodic table mass. From moles to molecules, I need my Avogadro conversion. Okay, So my periodic table mass has to be the mass of 1 mole of the formula. So I'm going to write here 1 mole of C9H8. That's the formula provided here. O4 equal. Now I have to do math. Where is my calculator? Since I have 9 carbons, so 9 carbons, 9 open parentheses 12 plus 8 open parentheses 1 plus 4 open parentheses oxygen is 16, right? So all I'm doing here is trying to figure out the mass of this formula, which I get as 180 grams of C9H8O4. So just on the side note, what I did to figure out the mass here was I used the periodic table mass. Of course, I shorthanded it. So I did 9 carbons. Each carbon is 12 plus 8 hydrogens. Each hydrogen is 1 plus 4 oxygen. Each oxygen is what? Oh, I put O for oxygen. Oh my goodness, I'm not being consistent. My bad. Let me go back here. Each oxygen is what? 16, right? So I'm writing the abbreviated form, but yeah. And adding all these up gives me 180. I hope that's correct, right? Hold on, it's dark in here. Hold on. Okay, much better. I know. I have the wrong light on. Anyway, so I have 180 grams. So I have this conversion written down here. I need the Avogadro conversion. The Avogadro conversion is always a 1 mole of any formula. In this case, my formula is C9H8O4 equal to, and it always has to be Avogadro number, ergo the Avogadro mole conversion, which is 6.022 times 10 power 23. Since I have a compound, I have to use the word molecule. You cannot use the word atom with compounds. Took me a while to figure that one out. C9H8O4. Okay, so once I have these are my 2 conversions. So before I set up my conversion table, I had to do a unit mapping thing. Okay, so I'm going to use my highlight here to follow along my units. To make sure you have the right number of conversions, when you check over this, you have to see the same unit twice. Okay, so the first obvious one is 1 mole here, 1 mole here. So I've seen the unit twice. So I have enough conversions for mole. Okay. I see a gram here, but I don't see another gram. I mean, of course, it's here in the past, but this is not what I'm checking. I'm checking the numbers of the units I have, right? I see a gram here. I don't see another gram. The closest thing I see is a milligram. So I need to find a conversion between gram and milligram, and that will give me a total of 2 gram units and then a milligram, 2 milligram units. I'm going to write this down here. Gram and milligram. 1 gram equal 1,000 milligram. Okay, this is in general. Okay, now I can apply it to this and I can say 1 gram of C9H8O4 equal 1,000 milligram of C9H8O4. Okay, so looking at this here, now I have a second gram to map with that gram, and then I have a milligram to map with this given milligram. So I have 2 moles, 2 grams, 2 milligrams. What about molecule? Molecule, well, this molecule term here, I guess you can match it with the wanted molecule right here. So now I have 2 of everything. So when I set it up though, since realistically there isn't another number, there's no number here that goes with molecule, everything will cancel out and leave us with the desired unit, which is molecule. So you start with the given unit, given number and unit. So I'm going to start here with 325 milligrams. Once you figure out how to do this one here, it becomes a lot simpler. When I was learning this, oh my goodness, it seemed like I would never figure it out. Okay, so I start with my given number. I'm done with this part here. The unit I have here drives my next move, right? Because I have milligram, I have to pick a conversion that has milligram in it, which would be this number right here. And I put the 1,000 milligram on the bottom of C9H8O4, and then 1 gram of C9H8O4. This drives my unit. Next, so I'm done with this. This unit here drives my next move. I have to pick something with grams of C9H8O4. That will be this one here. 180 grams of C9H8O4, 1 mole of C9H8O4. Okay, so grams and grams. I'm only canceling out the unit, by the way. And then finally, I have my Avogadro's number, so I have to use this one here. I don't have a choice. 1 mole of C9H8O4. And then here I have 6.022 times 10 power 23. And then here I have the word molecule, but I don't have any room, y'all. So over here, imagine this is molecules, right? Everything cancels out except for the last word. So I know when I work it out, I'll get some number, and then the unit will be molecules of C9H8O4. Now all I have to do is multiply all the numerator numbers, divide by the denominator number, and I get my answer. So 325 times 1 times 1. I could leave the ones out. Times, open parentheses, because I have a scientific notation, number 6.022, exponent 23, to the right, close parentheses, divided by 1000, divided by 180, and I get this number, 1.09 times 10 power 21 molecules. Okay, make sure you're multiplying all the top numbers. So 325 times 1 times 1 times, open parentheses, 6.022 times 10 power 23, close parentheses, divided by 1000, divided by 180. And this is what I got. So let me check my answer against their answer real quick, and then we'll see what we have here. So they gave you the plan, right? Remember, this was the original plan, but we have to add this to make our number match the starting point. It's almost like puzzle, like board games, right? When I view this as board games, even though I'm not the greatest at board games because I stopped investing a lot of time in learning those. So I don't really know a whole lot of those. When I was a kid, I used to really enjoy those, right? And I put my investment instead in school. Anyways, yeah, so you can't start if this pathway requires the first number to be in grams. You can't just pick any number given to you in the question and then put it here. The number has to match the fulfillment of the path, right? So you only get to use this if it's in grams. That means if your number is in any other unit, you have to convert it to grams. Okay, they work it out here and they get this number, the number that we got. Okay, and then of course you have a whole two-part conversion. So I want to do one more problem here as I talk about the whole two-part conversion. You can go ahead and figure out. So I would suggest, because this is one of those learning goals, that you know how to do the part to whole relationship as far as the mass is concerned. So we're told here there is a mass percent composition, right? Now, composition is talking about what is inside, what's the ingredients. I recently wanted to make something to eat. It's like a stuffed mushroom thing, and I'm like, okay, I'm trying to, do something different, explore new recipes. So I have to find my ingredients, right, for that stuffed mushroom, including a mushroom and other things. Anyway, ingredients are essentially the composition of what's going to be in my food. So in this context here, our elements are the ingredients in the whole compound. So they want to know the ingredients relative to each other as far as mass is concerned. So in this section here of the chapter, what you're seeing is a mass, or I should say a part to whole relationship, like the part of the ingredient, which would be the element versus the whole. So there are two, I want to say there are two major parts. I mean, there's so many different parts to whole relationship because all you're focusing on here is the unit, but there are two major ones that we will be focusing on. So the first one to tell you here is the mass percent composition, where they're telling you calculate the mass percent of chlorine in freon. So freon is a chemical used in refrigerant, right, to cool the refrigerator. The part to whole relationship that we're looking at here is, as it says, mass percent. So I want to focus on the mass relationship. Since we're looking at the refrigerant, I'm going to write the formula here, C2Cl4F2. Yeah. In this compound, we have 2 carbons. We also have 4 chlorines and we have 2 fluorines. Okay, so as far as the ingredients of the compound are concerned, there is carbons, there is chlorines, there was fluorine. So imagine that you were trying to build this compound. You have to get carbon, chlorine, fluorine. And then what relative amounts? 2 to 4 to 2. Now they want these amounts represented not in mole amounts, but in mass amounts. So what we're going to be doing here, they're telling you to find the mass percent. So trying to find the mass percent. The mass percent is essentially of chlorine, since they said of chlorine, will be the total mass of chlorine in the compound over the mass of the compound. Okay, so back to my ingredient. I'm trying to make stuffed mushrooms. So I have to figure out, well, how many mushrooms I want in the whole mushrooms that's going to be stuffed. So if I'm going to figure out the percent of mushrooms, I have to figure out how many mushrooms I want over. Now the only ingredient will not be mushrooms. So there'll be mushrooms, there'll be stuff in it that I stuff, right? Or I guess they have to have cheese. So I have to figure out how much cheese do I want in the whole mushroom that will be stuffed. I know this is like a whole thing, but you're trying to figure out how much of the ingredient do you need to make in the whole. So we are focusing here only on chlorine as part of a whole. So find the total mass of chlorine, find the mass of the whole compound, then you can see how much chlorine there is in the whole compound. Now it says percent. Percent usually means, over 100. So when we get this mass of chlorine over this, the whole compound, you then have to multiply this by 100, and that will give you that relationship in the percent form. Okay. So over here, let's see, our focus is this. So mass percent of chlorine will be 4 chlorines over this whole compound, which has 2 carbons plus 4 chlorines plus 2 fluorides, right? So let me see. I have to figure out what these individual masses are. Where's my periodic table? Okay, so 4 chlorines. 4 chlorines is 35.5, 35.5. 4 times 35.5, okay? And then 2 times carbon is 12, plus 4 times 35.5, plus 2 times fluorine is what? Approximately 19. So I'm using the abbreviated versions of these masses to make my life easier, okay? The top number works out to be what? Let me multiply this out. 142. The bottom number works out to be some number, 142 plus some number. So 2 times 12 will be what? 24. 2 times 19 will be what? 38. 19 times 2. Yep, 38. So I can now actually take the top number, 142, divided by open parentheses. The bottom number is 24 plus 142 plus 38, close parentheses, and then multiply this by 100, and I end up with 76.3%. Okay? So I have figured it out. If I take the total mass of chlorine divided by the total mass of the compound, what percent I get, right? I get 76.3. That's a lot of chlorine in the compound. So chlorine is obviously the dominant ingredient, right? It's very chlorine rich. Okay. So I guess they rounded up the numbers slightly differently than I did. Because my numbers, yeah, I over rounded them up. But anyway, this is what I got. Let me make sure 2 times 19 is 38, and then 2 times 12 is okay. Let's see, 142 divided by 166. I'm trying to figure out why my number is so different from theirs. Okay. I mean, I rounded up slightly different from them, so, but yeah, this is the answer they got. So they got the bottom number to be that, and then the top number to be that. I think I added the bottom number slightly differently. let's see, hold on a second. 142 divided by open parentheses 24 plus 142 plus 38. Okay, 69.6. I was wondering why there was a huge difference. 69.6%. Okay. So the setup was correct. I just somehow added the bottom number differently. But yeah, 69.6%. Yeah, that's more like it. And even though I rounded it up, the answers should be pretty similar, not that different. So yeah. Okay, so once we have this, now remember the conversion factor, right? I told you a part to whole conversion factor as far as mass is concerned. So you want to be aware, quick recap, conversion factor. So mass of a part to mass of a whole conversion factor. And so this one here, we just have the mass of the part over mass of the whole. Okay, so this is one of the conversion factors you have. The second conversion factor you have is moles. So in this part here, they're talking about conversion factors from a chemical formula. You can have two main types, mass to mass and then moles to moles. So from this part here, I'm going to show you the mole to mole conversion factor. Mole to mole conversion factor. In the mole to mole conversion factor, what you see here is moles of part over moles of whole. So moles of part over moles of whole. Okay? So you want to be able to take the part from the chemical and figure out how many moles from that part provide the whole. Okay? So for this part here, I'm going to be going all the way till the end of the chapter. And then when I get to the end of the chapter, no, actually, I'm going to be working this one more problem. And then after I'm done with that, I'm going to go and start with the next chapter. But I'll just wait to start the next chapter. Okay. So let me go ahead and just finish this part out since I already started it. It's important when you're given a chemical formula to tell what the ingredients of the part are in the whole. Okay. So our focus this time is not the mass. Our focus is the moles. So given this different kind of formula here, carbon, one carbon, two chlorines, and one fluorine, what is the molar amount of each? So we're going to be practicing how to get the moles of the part to the moles of the whole. You have C, Cl2, F2. This is our formula that we're using to practice. Okay. You can tell from the formula here, the subscript is 1, 2, 2. So this formula is made up of one carbon, there's two chlorines, and then there's two fluorines. Okay. So that's what the ingredients are to make the whole compound. If they want you to get the mass relationship, of course, you go and find the periodic table masses and then plug them in here, then you get the masses of the whole, right? But our context here, or the skill we're trying to learn here, is not the mass to mass relationship. We're trying to learn or illustrate the mole to mole relationship. So here we're seeing, I'll do it for carbon, okay? So for carbon, our mole relationship is mole of carbon over mole of the whole compound, CCl2, F2. Okay? And when you look at this formula here, we essentially have 1 mole of carbon required as the ingredient. The amount required for carbon in the whole compound is just 1. It says so right here. For each one compound. So 1 mole of carbon for 1 mole of the whole compound. And then for chlorine, we need 2 moles of chlorine to make one compound, right? To make 1 mole of the compound CCO2F2. And then for fluorine, we need 2 moles of fluorine to make 1 mole of CCO2F2. Okay? So remember, this molar relationship that we have here is based on the amount that you need of each ingredient or each element in the whole compound. And the amounts are different depending on how the chemical formula is written. For chlorine, for carbon, 1 amount of carbon for every 1 amount of the formula. So the amounts here are mole, then mole, and mole. If the amounts are something else, if it's molecule, right? For chlorine, you need twice the amount of chlorine for every 1 formula of the compound. For fluorine, twice the amount for every 1 formula of the compound. Okay? And then once you have this relationship here, then you can use this relationship in the problem. Okay? And of course, you skip over here and look at this problem here in the context of this problem. So I'm going to work out this problem, and then this will be the end of it. And I'll be done with this chapter. You can look at the rest of this chapter later on. Okay. So once we have a once we have a mole to mole relationship here, now we're moving over to this question. Now the issue with this question is we talk about, well, from the formula you can get 2 relationships, a mass to mass relationship, a mole to mole relationship. Is all about part to whole, right? But when you get to this question here, they're telling you problem solving, right? Which chemistry is all about that. Using the chemical formulas as a conversion factor. Now we're told here we're using mass percent composition as a conversion factor. So they're telling you that you're going to be using a mass relationship as a conversion factor. Let me scoot this over here. Okay. Now, as we read the question, even though it is wordy, don't get lost in the words. Because they're giving you the context, focus on the context. When I was a student, I used to get lost in words. Words aren't my strongest suit. Even though I talk a lot, I know this was like a walking oxymoron. I communicate using language, but when others use language, I need clarity. Like they can use words, but if they're not being clear with their words, I usually have to ask a lot of follow-up questions to get clarity. Okay. So when I'm reading the question here, if I feel like the author of the question was not very clear, I want to find the address and email them, and have this whole dialogue. So I've learned since then to kind of help myself, right? Because I'm not always going to have access to the author or the person who is writing, and use the context to really answer my own questions, right? So as we're going through here, the title is the context. It's telling you we're going to be using mass percent composition as a conversion factor. So we're going to be converting, right? Using what? Mass and then percent. So that kind of helps to frame my mind. So even if the author is rambling on and what I personally decide is unnecessary information, I have gotten the bottom line here. Conversion using what? Mass percent. Okay. So it started to help me a lot when I was solving chemistry problems. When I see word problem, I'm like, I'm not going to be overwhelmed by all the words used. I just find me a title and it gives me the context and I can pick out what's important. The US FDA, the US Food and Drug Administration, recommends that a person consume less than 2.4 grams of sodium per day. Okay. Since I know the context is, the plan is we're going to be converting something, right? But we're going to be using mass. Then the first mass I see here is important. 2.4 grams. And they said of sodium. So I need to know what the chemical is of sodium. And it says here per day. So as I'm reading this, I'm not sure if the time is important. What we're covering right now, the time really hasn't been important, but I'm going to write the per day just in case, because I don't know if I need it. So I'm underlining here, but I know 2.4 grams of sodium, that's important. What mass of sodium chloride? Ooh, okay. This is given, and my wanted is grams of sodium chloride. So before I continue reading the stuff, I'm like, wait a minute. Sodium is in sodium chloride, but sodium is only part of sodium chloride. So the grams of sodium they gave me here is the grams of the part. So you see how I'm beginning to now piece it and match it to what I just learned? And then they want me to get the grams of sodium chloride. Sodium chloride is the whole compound, but sodium is only part of the whole compound. So they want me to get grams of the whole. Okay, so what I'm seeing here is they gave me grams of the part. They want me to get grams of the whole in the context of this application problem. Okay, so I'm right here. And then they said I should get it in grams. Okay, so I wrote here in grams. I assumed in grams. I shouldn't have assumed. They said in grams. Can you consume and still be within FDA guidelines? Right. So the message is we are recommended to eat less than 2.4 grams of sodium per day. What mass of sodium chloride? Sodium chloride contains sodium in grams. Can we consume and still be within the FDA guidelines? And then we're told sodium chloride is 39% sodium by mass. Oh, so now we're given a relationship between the given and wanted. Oh, we're given a relationship. Okay, so we're told sodium chloride is 39%, like a grade, right, of sodium by mass. Okay, so for me to solve this problem, to figure out what grams of sodium chloride is, I have to decode what a percent is, right? Because these are the words, but I need units. If I say you got 39% on the exam, that will not be good. But we understand that 39% is essentially 39. The percent, cent stands for 100. That means you got 39 over 100, right? So I'm just converting this to a usable form. 39 over 100. Okay, but they said by mass, right? So by mass means it's not 39 points over 100 points. It's 39 mass unit over 100 mass units. Since everything else here is grams and grams, make this one also grams and grams, grams and grams. Okay, so I'm doing well. Last thing, they said it's 39% of sodium by mass, meaning that in the whole compound of sodium chloride, in the whole, 39% of that mass came from sodium. In our fraction, in our conversion fraction, we always put the part on top and then the whole on the bottom. So we tend to put it that way, part over whole. That way, 39 grams belong to sodium, and then the 100 grams belong to the whole, sodium chloride. So all that dialogue just to say 39% of sodium by mass means this fraction here. So I can now look at my number again, right? After I've decoded this and say I was given the grams of the part, I was given their relationship, the part to whole. Now I can use those two numbers to figure out this part here. Okay, I'll set it up. When you're doing your conversion, start with the simplest number. So a fraction is a lot more complex than a simple number like this, the given. So I'll start with my 2.4 grams of sodium. Okay. Now I use this percent as a conversion factor, but you know the rules of using this conversion bracket. The unit and symbol up here must match the unit and symbol down on the bottom diagonally. So if I have grams of sodium, I have to have grams of sodium down here. If I'm going to use this, I can't use it in this form. I have to flip it to use it according to the rules of this bracket, right? So when I flip it, my grams of sodium end up on the bottom, and then so does 39. Then 100 grams of sodium chloride ends in the top. So what seemed like an ambiguous question about the FDA trying to control our lives and control the amount of salt we take, they're not controlling. They're trying to make sure we're healthy, okay? Because it costs the government money if we are unhealthy. Anyway, yeah. So it's not really a question about the government trying to control how much sodium we take, but it's really about using the mass relationship to solve this problem, right? Now that we have that, we have grams of sodium, and then we get our answer in the desired unit, grams of sodium chloride. So with this, you have permission to go buy McDonald's fries, right? Anyway, this is kind of how I try to look at it sometimes, try to make it about me. Like, how many fries can I eat? 2.4 grams of sodium times 100 divided by 39. Okay. Spit 6.15. Yeah, 6.15. So we can eat 6.15 grams of sodium chloride. That's actually a lot. I mean, it's a lot, but again, it's not. There's some meals where I eat and I look at the amount of milligrams. They usually write the sodium amount in milligrams on the box, and I'm like, I can't even taste the salt. Where did they put this salt? I can't taste it. They could have left it out. Then my husband tells me, oh, it would have tasted a lot worse if they had left it out. Anyway, so we can eat a whole 6.15 grams of sodium chloride and still be within the limit they want us to have, which is a maximum of 2.4 grams of sodium. Okay, so work it out over here. Yeah, they rounded theirs up. If you eat all of the sodium, you're still within the guidelines. Okay, so remember the point of this, once again, even a question like this, it has a lot of dialogue, but at some point here in this question is a part to whole relationship between the part, which is I guess in this case it was hydrogen, and then the whole was water, right? Because it's talking about hydrogen. I won't work this one out here. It's just an additional problem to work on. But remember, this is all about problem solving. Yeah, I see here in the conversion at some point they have a part to whole relationship as far as moles is concerned. The rest of this chapter talks about empirical formula, molecular formula. These tend to be a lot more easy to follow. Just follow the steps. They show you step by step how to find the empirical formula. You can follow the steps and figure this part out. I want to highlight the most difficult parts of this chapter. So I feel like I've done that. So with that, I'm going to close this one out and then start the next chapter, because you do have a lab that was due this weekend or at some point. So I want to go ahead and start the next. Wait, what am I closing out? Oh, I have to stop the whole video. I forgot.